That's just okay. Now, carrying on from what we were doing yesterday, as you can imagine, I give you a basic one-nomen architecture. Let us just dwell upon that a bit more vividly. So, you can imagine this is a logical diagram. Obviously, this is a logical diagram. So, in this one, which is generally termed as the central processing unit, okay, or CPU. Now, mind you, not only is the CPU called the CPU, but also the tower in which the motherboard is, as you can guess, the box where the motherboard is and all the peripheral devices are. That is also called the CPU. Okay, but here we are only we are only terming CPU. We are only terming the processor as the CPU. Now, obviously, it has got some. So this control unit. This has the digital logic that controls. These are the digital logic that controls the rest of the work. And I'm just repeating what I just shown, and then I'm going to be elaborating this a bit more. There is the arithmetic logic unit. Arithmetic logic unit, or ALU. This is the arithmetic logic unit, and these are the registers. I'm drawing them like this because they are just memory. There's onboard memory, very fast ones. They are attuned with the ALU, and this ALU contains. So one register is considered logically to be a part of the ALU, which is the accumulator, and these are all data registers. Mind you, as we said yesterday, that data here means data as well as instructions. So these are the accumulator. What is the accumulator? Whatever is done in that. In the A loop section, it has adders, subtractors, so shifters, comparators, etc., etc. Okay, several different digital logic, so etc., etc. There are lots of different types. All of these is here concerned with the performing of arithmetic and logical operations. Arithmetic operations, for example, plus, minus, division, multiplication, modulus. Okay, logical operations, for example, greater than, lesser than, greater than, lesser than, equal to, greater than, equal to, okay, or equal to. Then also things like logical and, logical or, logical nor, then x nor, etc. All of these are logical. So this unit, okay, so is called the arithmetic logic unit. So this is there. Now you might ask, okay, sir, in that case, what is there? What all is there in the control unit? The control unit, okay, sends out control signals. Okay, like for example, now this is connected by way of several different buses are there. The most important of those two, or rather, I would say not most important. All the buses are important. The most prominent of those two that what we are concerned with, when especially when we are programming. Let's say this is the working memory. This is the working memory, or called the main memory. And these are all the lines where data is residing. So you see, this is a big place made out of transistors. Whatever technology it is made out of transistors. Obviously, the technology is improving every day. There is now, for example, RAM is, for example, a working memory. It's the main memory where all the programs are loaded, the data are loaded. and the instructions are. How the instructions are drawn in? First of this is the address bus is there. The address bus, the address comes from the control unit. Where does the control unit get the address from? Well, for example, amongst the registers, there is a program, there is the the instruction register is there, where the instructions coming. Then the program counter is there, where the next data is coming from or instruction is coming from, etc. It gets it from there. Now, for example, let's take the program counter, for example. Now obviously this is a big part of memory. So if you're putting some data in there and some instructions in there, it will be lost to you. So you must be able to locate this. How do you locate that? Answer is by assigning line numbers. Obviously this is in decimal I'm writing, but obviously it's not in decimal, it's in binary or hexadecimal. It's in binary. I'm just writing it in decimal so that it's relatively easy for us to understand. So all of these are numbered and these are lines. Now these line numbers, they are the memory addresses. These are called the addresses. Now let us say that in the program, obviously this is run by a program. Now in the program it is mentioned that the first instruction is coming from some place, say here. Then it got two data. Let us say they are at 5 and 6, D1 and D2. Then the program counter will act like this. It will be loaded with 4. Okay. Then the next instruction will be at, say, that's 4, 5, then 7 will be the next instruction. Some instruction is there and some data is there, like that. We are assuming that there are binary instructions, that means they take two data, the instruction data, instruction data. The program counter will be, the next instruction will be at 7. The data are at 5 and 6. And the data for these are at 8 and 9. Okay, and this program counter is adjusted accordingly, okay, by incrementing it, so that the control unit will automatically consult the program counter, give out the address. The address will select the particular line through the address selection logic, and once that is selected, then data will flow into the computer, or it will flow out to the memory from the computer. So that is why it's a two-way bus. The data bus, you can imagine, it's a two-way bus. Data can be stored, data can be retrieved. From memory, data can be stored to memory. That is why it's a two-way bus. Okay. So that is exactly why address bus, where bus refers to the data lines, is one way, and data bus is basically two-way. We can say that address bus is simplexed, data bus is duplexed. This apart, what all can be there? Several other control lines can flow out from the CPU to the memory and to the other places. See, there's not just this memory. There are different types of things. For example, there is a concept called DMA, direct memory access. So you need a controller for that. That is the peripheral device. You need an interrupt controller where there are interrupts from different uh, you know uh, subroutines and routines. Interrupt means there is one routine, say it is going on, and it needs to interrupt the computer for some important work. For example, you are maybe doing some internet work or some word processing, and suddenly then there a new file has come in from the internet and that needs to be checked. So that is exactly when the processor needs to give time to the antivirus software. Otherwise, your computer's security will be seriously uh, compromised. So as such, what will happen is it will ask you it'll ask you to just go for. I mean, then that CPU needs to be interrupted while it is doing the current work, and it has to put the current work on hold in a steady state and then go to the particular program that needs to be run to do the important work and come back again to the work that is the current work at the moment. So this is called interrupting. So interrupt signals have to be generated. So lots of different signals come out from the control unit. Not just these two, not just these two. Lots of different other signals come out. Lots of different. So there is the address bus and the data bus. Plus there are several buses coming out of the control unit. Several other. Let me just draw them in blue. Okay, so several other sort of control signals coming in and out of the various devices, peripherals, into and out of the okay uh, CPU. So these blue lines are all those various signal buses. Okay. So signals in and out, including control signals. And obviously, these also include, okay, so signals in and out, these also include the clock. So at some point of time there is a clock. You have now done some of sequential logic, and you know that the clock rate is the clock pulse is very important to activate the flip flops and the registers inside there, and the other circuits which are synchronous in nature. They need to be clocked, and also the CPU needs to provide some clock out also. So clock in and clock out are also there. Why does it need to provide some clock out? Because if it wants to sync some other device with it, then it needs to have the clock out. I'll give you an example. If the control unit is working at X and a device that the control unit is working with works at X plus 10, then it is faster than the CPU. However, if it is faster than the CPU, then the CPU cannot cope with it. Once again, if the device is X minus 10, then obviously it is slower than the CPU, and then the control unit will wait for then the device cannot wait. The device cannot keep up, so the control unit will wait for it. The CPU idle time, we call it, when the control unit is waiting to do something but doesn't have enough instructions or data to perform it, or enough signals, enough ready signals to perform it. In any case, that is waiting for some device to stop working or for some data to arrive or whatever. This is called CPU idle time. So CPU idle time is something that should be avoided very much. Okay, so just to mention, it's called CPU. So CPU idle time to be avoided. So CPU needs to clock other devices. Which are the peripheral devices? The peripheral devices, so that they can work with it. So the devices have a range. They don't. When they are made, when the peripheral devices are made, they are made to work with a different variety of CPUs. You see, so it's so let us say they have a range from X. Say if the CPU speed is X, then the device may be the range of the device may be X minus 10 to X plus 10. Now you see there is a CPU 1, different kind of a CPU that works with x plus 5, then the CPU that works with x, and then there is another CPU, say CPU 2, that works at x plus 50. So in that case, as you can see, and then there is another device, another CPU, say that works, the CPU say 3, that works at x minus 50. So this is a slower CPU, this is a much faster CPU. These two CPUs are within range. If they provide the device, say if I draw the device like this as a hexagon, just to make sure. Okay. Then what happens is that, so this our hexagon device is there. Let me logically show you how the scheme may mark. So this device has a range of x minus 10 to x plus 10. Okay. Now the CPU that is working with, let us say it is CPU 1, as I say CPU. Now CPU will provide the clock of x and the device sets itself to x. CPU 1 will provide the clock, its own clock, and the clock is x plus, so what is CPU 1? X plus 5. So x plus 5, and the device will set it to x plus 5. It's got a range, is within the range now, so that's okay. When we are coming to CPU 2, however, if it provides it with its clock, it won't work because CPU 2 works with x plus 50, which is beyond the capacity of this device. So the device will always be set to highest mode, which is x plus 10, and the CPU will be idle. So in that case, you need some sort of a controller or a buffer of some sort. Okay. Okay. For example, data buffer. An example of that is the data buffer. What is the buffer? Buffer is the part of memory that holds intermediate data so that it can be worked with later on. Okay. So now what will happen is the CPU will provide the, for example, the CPU wants to provide the device with some data, but it is working at x plus 50. This device cannot work with x plus 50, so it will set at x plus 10. What the controller will do is, it will then controller or the buffer or whatever it is, what will do is it will act as a go between. So CPU will provide the data, that controller will actually buffer up the data, and it will keep on providing the data to the device so that the device may show it one by one. For example, a very good example of this is, for example, a multimedia stream. If the CPU, if the graphics processor is providing fast data to say, and this device is, for example, the input output controller, which is, for example, or let us say it's an input output device. Now the input output device can only work with x plus 10. So what happens when the CPU data arrives? It is not ready because it is working at a very slower pace. So basically it is still providing with the output when the next data arrives. So how will it handle? The answer is a controller. The controller will buffer up the data and it will provide this device at x plus 10 rate or whatever rate it is that is comfortable, then it will be providing it with that. Similarly, if you have got a CPU which is working at x minus 50, again you need a controller in between. Why? Because it is working at x minus 50, the device can only work at x minus 10. So even if you set it at x minus 10 and give it to then the CPU works at x minus 50, so there will be a mismatch, the data will be lost. So what happens is, gives it to the controller buffers it, and then in a controlled fashion it provides it to the CPU for collection and processing, whatever processing it has to do, and then again it gets it and then gets the data from the CPU and gets it to the device. So basically the controllers make life easier for us. A direct relation between CPU and an input output device or an end device is basically, or the end of the computing or the end of the end of the processing a device is obviously a very bad idea of a design, very bad idea of a design. That is exactly why there always are controllers. There are interrupt controllers, DMA controllers. There are lots of different types of timing controllers, clocking controllers. All these are there. Even the clock may come, even the clock that is coming into a CPU, this clock here that is coming into a CPU, if there is a clock mismatch, then that there will be a controller. There may be a controller there also. And you see, uh, clock is again most important because you see the data. So, for example, in a von Neumann architecture, data and instruction is basically of the same sort of format, the same type, except that the pattern match. It's of the same format, obviously, because the size is the same thing. So data and instructions are the same format. So for example, now let us take in a simple case, it's all numerical in nature. Okay, operations, they are in the form of opcode, and okay, these are obviously the instructions. The instructions are to operate on something, to operate, and then there are the data, which is obviously numeric, also numeric. Now let us say that addition 5 and 5. It may be that 5 is the code for adding also. 5 is the code for adding also. In that case, it poses a big problem. There is an ambiguity. When you write out the instruction, it looks like this: 5, 5, 5. So how will you know, or how will the computer know what is what? The answer is that it takes the first one to be the instruction and the next two to be data. So this format is specified as follows. There can be unary operations with just the code and nothing else. There can be, there can be, I beg your pardon, there can be implicit operations, unary operations with just the code and just another data. There can be operations which are binary in nature, for example, with code and data and data. If they are trinary, then there is another data. The ternary, then there is another data. And then there are these explicit operations. For example, shutdown. There is only a code. Normally we deal with unary and binary data. Some data are ternary also. And these data, these codes, the implicit codes, for example, shutdown or clear screen or something like that. Just one code that is enough to do the work. No data is explicitly required for that. Data is implicit. So there is this instruction format as well. The instruction format can be specific. So this is basically This is instruction format. An example that I've given you from 8085 Intel microprocessors. Okay, these are byte length codes. Each of these boxes that you see are a byte each. This is an 8085 instruction format. So there are different other formats that is available with different other CPUs, different other designs, different other formats may be available. Now, why the timing is important? You see, let us take this into account. So 5 plus 5 plus 5. I'm sorry, 5 plus 5. Okay. Now this instruction format is as follows. This is the operation, these are the data. So op, data, data. Now you see the internal operation table contains the opcode and it tells what is the type of instruction. Now for example, if it's a ternary data, then if you have 5 plus, so if you have 5556, it means these are all data. How do you know that? By understanding it from the looking up the op table. You don't look up, the computer looks up. The logic of the computer looks up and knows that this is ternary data, so it expects this. However, this is for ternary. Now what will happen if it's binary? Then this is 5, 5, 5, 6. It knows that this is an instruction, this is the data, this is the data, this is an instruction again. It will take it as an instruction because it is binary data. So if it is binary, it ends here, and this is the start of another instruction. For ternary, it was sure that the 3 would be the data. Binary, it only has 2 data, so obviously it means that this is another instruction. Similarly, if you go for unary, what will happen there? Immediately, when you have 5, 5, 5, 6, it considers this to be the instruction, this to be the data, this to be another instruction, and this along with others to be. If this, on the other hand, if 5 is unary, then obviously this is also unary. So these are the same instructions. We are taking 5 only. So it's the same instructions. Let's consider this to be the data of this. Consider this to be the data of this, etc., etc. These are bunched together. This is why, and if it is explicit, then let us say if it's just 5, it considers this to be the end of it. Whatever is coming next, for example, if you give it a 6, then it is considered to be another instruction. Now you can imagine that the position is very important because 5 here is a data, 5 here is an opcode. 5 here is a data and 5 here is an opcode. You can imagine that 5 here is the end of the data list, but 5 here is the middle of the data list, depending upon whether it is ternary or binary. 5 here is a repetition of this operation. 5 and 5. Repetition of the operation because it's unary. So depending on the position, the instruction is decoded or the instruction is carried. Depending on the position, it is either an opcode or a data, an opcode or a data, an opcode or a data, an opcode or a data. Now, how does the computer tell this is the first one, this is the second one, this is the third one, this is the fourth one? Answer is timing. So we will learn something called the timing diagram, which will show us. For the timing, this is it. I'll give you a very basic view of it. Let us say the clock is going, as you can imagine, just brushing up your knowledge. There are several edge triggered and level triggered devices, but edge triggering requires an RC circuit. So we try to build in some more digital logic so that we can use a level triggered clock pulse as an edge triggering. Now we have seen this in the master slave JK flip flop. We have seen this in the direct coupled JK flip flop. So similar devices are abundant. I mean, because edge triggering is always a bit of a problem in an IC. We just use the levels and complete the edge triggering effect. Completes the edge triggering effect through the use of additional circuitry. Now let us say the clock is this. I'm not making it very even, unfortunately, but obviously this should be very even. Let us use the clock. Now let us say we have the data in. When the clock rises, we have another data coming in, another data coming in, another data coming in. And you see, you can very well imagine that if it is ternary, then this would be an operation. This will be a data. This will be a data. Sorry, binary. If it's unary, if it's ternary, then it will ask for, it will wait for another clock pulse for the third data. If it's, on the other hand, if it's unary, then if this is taken as the opcode and this is the data, then this again will be taken as the opcode. So how is this? This is first, this is second, this is first, this is second, this is third. How is this first, second, third differentiated? Because of the clock pulse. First clock pulse, okay. So these are T cycles, and this is one machine cycle called M. Clock cycles are called T. So T1, T2, T3, etc. Machine cycles, they're called M. The first machine cycle shown. There are other signals that can happen simultaneously with the clock, and they will be timed. So this timing is very important. No clock, unfortunately, the total thing will go into disarray. So this timing itself tells the computer rather, not us, the computer rather. First clock pulse, the data comes in, is operation. Second clock pulse, according to this, it will be either another operation or a data. Third clock pulse, according to this, will either be another operation or a data. Fourth clock pulse, according to this, will either be another operation or a data, and so on and so forth. Then in that case, that will be a separate machine cycle altogether. So this is how it works. So you see, timing is so important here. Without timing, this won't work. And you might wonder, why don't we write 5 plus 5? We write 5 plus 5, but in a computer we write it as plus 5 5. Why is that's the case? Why is that the case? The answer is this operation specifies the circuit. Imagine what was happening here. What was happening here? That when the clock was going faster, when the data was arriving, the device was not ready, the data would be lost, so we fed it to a controller. So similarly here also, If 5 arrives and the circuit is not ready, 5 will be lost. What am I going to do with only one 5? So we mentioned the instruction first. When we instruct it through things like that, the different types of, so there is some various different logic. There is the instruction encoder, there is the instruction decoder, there are the control matrices, etc. Through that, through a combination of these, whatever circuit is to be used, the the opcode for this is recognized because it is coming in the first clock pulse of the machine cycle, recognized as an instruction, goes through the instruction decoder, and through the control matrix, it, or it may just be through the control matrix, whatever is the case, it will just activate the proper circuit. And soon as it activates the proper circuit, circuit is not ready to receive 5. Let's say it's an adder, obviously it's a full adder list. So it is ready to receive 5 and then 5. Either it will be parallelly added or serially added as the adder is there, is, but if it's a parallel adder or a serial adder, that will work there. Answer there we are. So this is very important how it is. So this is basically the 8085 and its similarly typed processors. Whether the obviously 8085 is a very old processor. We don't use that except for educational purposes. Many institutes don't even use 8085s. They may use 8086s or they may use Spark or something else. But normally speaking, now it may be different. I'm saying that this may be different according to the arrangement of the circuitry. It may be different, but normally this is the case. The first one is the opcode. Okay, so this is the general case. So generally, there may be specific cases of architecture where it is different, but general cases architectures always follow this, that the opcode is there, so it specifies the circuit to be turned on, and then we receive the data. It makes a lot of sense doing that. Now one example is when we are getting data from the main memory. This is main memory. Now you see, in this main memory we can write and read. So there are two buffers available. One is the input buffer, one is the output buffer. What do they do? The output buffer regulates the output from the main memory. If the output buffer is off, nothing can flow out, and you cannot read it. And if the input buffer is on, you can input. If the input buffer is off, you cannot input. So the CPU sends an IO signal. It may be arranged like this, that if it is low, then the input is on, if it is off. But then in that case, you need some other signals, okay, which tell you whether to read or write. Read write signals. And then there is the address that is coming in, and then there is the data which is coming in or going out. Now let us see how it happens in an 8085, for example, which is basically a very general case. That is why we study 8085s for academic purposes, that it depicts a very basic computer system which is generic to most of the design. So basically the CPU sends out an IO signal. Before that, so, and then it and also a read write signal. Sorry, beg your pardon. Uh, it won't be the IO signal. is the no, it sends out the read write signal. I beg your pardon. It sends out the read write signal. The IO signal can also go into the memory if it is actually getting input output sort of. Generally, it goes to the no, so sorry, the IO signal. Let's not draw the IO signal here. I beg your pardon. Just the read write signal. Now that's the so it sends out the read write signal, and according to whether it's read or write, if it's read, the output buffer is on. If it's write, the input buffer is on. Then the address bus follows through with the address. So the read write signal, there is a selection logic here that either activates the output or activates the input. The address bus, that there is an address decoder which selects only one line at a time. And then say if you are reading it, input buffer is off, output buffer is on, and when address is selected, that data goes out, not goes out rather, it is visible through the output buffer so that the signal is copied in the data bus. It is copied in the data bus, so it is arriving at the control unit, or rather, sorry, the central processing unit through the help of the control unit, and it is getting stored in some register with which you can either work or through an input output signal you can output it, or you can input it to some other programs and so on and so forth. So you can use it in another program. If it's on the other hand write, then the output buffer is turned off for the particular address. The output buffer is turned off, and when write is going on, input buffer is on, output buffer is off. Address comes in, and already the line is selected, and the data that is available in the register here somewhere, register or other part of memory or something. If it flows through the CPU, then it comes from CPU registers. If it comes from memory, then it comes directly from memory, from other parts of memory. It is whatever it is visible in that particular line, it is copied into the data bus, and it flows into the address that is specified here, and we say it is copied. Remember something, that there is something in, see, whatever is there, if you even delete it, that means it is made ready to be overwritten. Nothing is actually physically deleted here. Even if it is purged, it goes into some sort of a random state. So this is how data is transferred. And in all of these, if you want to just say, for example, if you're writing it and you arrive with the data, address is not selected, the read write signal is not selected, what will happen? Obviously, the data will be lost. If only after you select the address and put it to read or write, then only when you come with the data it will make sense, or then only you can read something meaningfully from the memory. So this is also another example where the operation, what is the operation going to be, precedes the data. Very simple thing. This is how normally the instructions are arranged. Now all these things, as I mentioned yesterday, they can come through in various sort of ways, and they can be implemented in various ways in different architectures. So you see, computer architecture, it's let us just look at, okay, now rather than me going on about it, let us just look at what Google has to say about it. So if you can read this screen, computer architecture is concerned with balancing the performance, efficiency, cost, and reliability of a computer system. The case of instruction set architecture can be used to illustrate the balance. So, okay, blah blah blah. Now, If you go a bit further up, let's see. There's no response. Okay, sorry, this makes more sense. So in computer engineering, computer architecture is a set of rules and methods that describe the functionality, organization, and implementation of computer systems. So functionality, that is what kind of functions it will perform. Organization, that is how are the logical circuitry arranged and what is the logical arrangement of it. And the implementation of computer systems, that is what are the devices that are going to be going in there. How is the actual computer, that is how is the CPU actually going to be implemented. What are the other devices that's going to go in there, and so on and so forth. This is a part of computer architecture. This is what architecture means. Some definitions of architecture define it as describing the capabilities and programming model of a computer, but not a particular implementation. That means, as for example, in the case with the book on Stallings that I quoted yesterday, that some what is saying in Wikipedia is some definitions of architecture define it as describing the capabilities of and programming model of a computer. So how do you what is the programming model? The programming model means when you're programming the computer, what are the registers you need to remember? What are the operations that are there? What are the registers that are there that you need to remember? And what are the capabilities? The capabilities is what are the functions that the computer will do. Okay, so so it doesn't mention a particular implementation. That means it is what is called a microarchitecture or an organization. It is kept out of the definition of architecture. So in other definitions of computer architecture, it involves instruction set architecture, microarchitecture design, logic design, and implementation. All of that. What is microarchitecture is actually the organization. Computer organization is the microarchitecture. Now, if you, now, so basically, there's a very good treatise of it here. You can have a read through this. Okay. Now you see the few things that have been mentioned here. For example, this instruction set architecture. How are the instructions going to be devised? What is the length of an instruction? How will the instructions appear? Is it infix or postfix or prefix, for example? Okay. And how is the instruction register going to be designed so that it will activate a particular type of circuit, which actually determines the opcode? Or if you first devise the opcode, then you have to make the fabrication accordingly. This is instruction set architecture. Microarchitecture means how are the devices arranged? How are the memory arrangements? What are those? How are the device arrangements? What are those? That's the microarchitecture. I mean, rather that is to say, not the device arrangement, but the memory arrangement. Yeah, also maybe the device arrangement also, and also things like what kind of gates are you using? What kind of, is it only NOR gates or NAND gates, or is it all sorts of gates? What kind of circuits and flip flops that you are using? All of that is a part of microarchitecture. So we can say there is if we can quote it from Google, instruction set architecture is for instructions, the design and implementation of instructions. Okay, how the instructions are going to be, what is the length going to be, etc., etc. Then there is microarchitecture, which is nothing but the organization of the computer, the digital organization of the computer, arrangement and everything else. And then you can go even you can go you can take it into even more uh, sort of different layers. For example, there is system design. That means how many processors, how many memory chips and what size and type, what and how many peripherals used, etc. So that's your system design. If you look at the treatise that is given in Wikipedia, you will see that you can divide into some further layers also. Microarchitecture, we see that it is the organization of the computer. And if you look at it a bit abstractly, there is something called macro architecture. As the name suggests, the organization of the computer in a more abstract logical sense, without going into uh, details too much, is a macro architecture. This is absolutely necessary uh, when you are discussing some bigger issues, etc. Then macro architecture is very necessary. Then you can also have assembly instruction set architecture. Do you guys happen to know what is an assembly instruction? Anyone? Anyone can tell me what is an assembly instruction? Guys, are you being able to? Are you listening to me? But you don't know what is do you know what is? Do you know? Have you ever done assembly language programming? All right. Assembly language basically you can say it is just a step above machine language programming. Machine language is basically in instruction sets. The instruction set programming is very hard for humans to do, so we'll use mnemonics. Like for example, instead of using opcodes, machine instructions would be in opcodes, as you can imagine. Rather than using opcodes, which would be too tedious for us, we use mnemonics for those opcodes, like for example add, move, load, etc., etc. Now we can use this, and an assembler is used to change assembly language into the instruction set, into the proper machine instruction set. Just like just like in case of C, just like in case of C, you have the compiler. Similarly, in case of assembly language, you have the assembler. So how the assembler is going to be? What are the assembly instructions? What are the assembly instructions that are supported? For example, in case of 8085 microprocessor, once again, it has got 80 assembly instructions. So that the architecture of that is the assembly instruction set architecture. Just like the machine instruction set architecture is the instruction set architecture of the processor. Similarly, the assembly language and the assembler provided, supported by the CPU, the particular architecture is called the assembly instruction set architecture. Then there is something visible to the programmer, that is the high level stuff, for example compilers, etc., which define a consistent interface. Okay, so when the compilers work, they have to work directly with the operating system, and sometimes with the hardware, etc., sometimes maybe with the hardware. So they need to have a set of instructions as well. So that is called programmer visible macro architecture. For example, for use with compilers. Then another thing is there, which is called microcode. Basically, it acts as a wrapper around the actual hardware. That is, it's not the exact instruction set, okay, but it is actually a software that translates the instructions that you give it into machine instructions by analyzing them. For example, Java virtual machine. When you work with Java, basically microcode is, you can view it as the interpreter. You know that there are compilers and interpreters, so microcode is basically like the interpreter. Java virtual machine, for example, has a microcode. So when you are putting in Java files, it is converted into the object file, the class file. It is compiled into the class file. The class file is then turned into the object file. Now, basically, this object code is it's actually visible to the Java microcode, and the object code gives instructions to the microcode. And what does the microcode do? The microcode analyzes those, that object code first, and if it is safe to execute, if it is legal to execute that. Legal doesn't always mean law wise. Legal means based on the platform what is legal or not. Then it executes that by issuing lower level instructions to the computer. Then there is something called UISA, and alongside that we have so VEA and OEA. These are like this. UISA is basically user instruction set architecture. VEA is virtual environment architecture. OEA is operating environment architecture. User ISA is basically they are for example used for RISC, reduced instruction set computers, for example, for use by system programmers or programmers in general. They use, these are the interfaces that are available to them for use. The virtual environment architecture is used for virtualizations. So if there are virtualization programs, I should spell it with a Z actually because it's American in nature. So virtualization programs, they follow the virtual environment architecture. And operating environment architecture, as you can very well have guessed, it is for the operating system developers. So operating system developers use this operating system environment or operating environment architecture. So what does it have? It has the low-level instructions or the interface that the operating system writers will use to write an operating system for that particular architecture. So obviously it depends upon the architecture, and the OEA will change as soon as the architecture of the computer changes. Then there can be several other types of layers that you can put in there, but one of the last of the important ones has been the pin architecture. It refers to the signal out, signal in pins. That means pin architecture, it basically refers to, okay, the pin configuration. So this is a processor here, and there is a pin there, the pin there, pin there. What signal is there? This is say S1, this is S2, this is IO.